Anyway, we're back. I have two things to show you today. I have a lab 4 that's functional and ready for me to put into checkout. I have 2 more robots and 1 more CC 1352 kit. So I will be updating the Google Doc about what kits are available. And Austin has asked me to give more information on the project, which I will think about and do on Thursday. Okay, so I want to do 2 things today. I'm going to show you lab 4, and then we're going to go back and do the HC12 again, because that's one of the simplest sub-gigahertz projects. Show you some more encoding schemes. But before I start, any questions? Okay, so I will be on campus probably later today.
Sorry.
Yep, I'm sorry.
I was muted. What about lab 3? If we, is there like a for sure lab 3?
Well, there's a whole bunch of lab 3. Okay, fine. All right, so go over here. Over here. All right, you can see my screen. There are. Oh shoot, there's some more. You're absolutely right. No, this one. Okay, there is one lab 3 that's completely fleshed out. And there is one of these kits in checkout, and I'm going to bring 2 more today. So Wi-Fi, yeah, Wi-Fi. I know that, okay, there is an unfleshed out this is one lab 3. It basically, it's you put a CC3100 on top of this robot, and it will do a IFTTT, if this then that, and log robot data onto the Google Sheet. So you set it up a hotspot, fetch the weather. It's, so you can fetch the weather. You can send an email from the robot, if this then that. Let's see what else. This is setting up if this then that, and then you could set up a triggered event, which will well, this was the email, but then you can set up a triggered event such that it will log into a Google Sheet. So you do it again, and you get it. It doesn't cost any money, but you do have to make an account. My recommendation, if you do this lab, that you create a dummy Google account, because somewhere in the process of this lab, you have to allow webhooks access to your Google stuff, and that's probably just a typo. So because when you do the okay, that's the mail log data. When you set up this IFTTN, it will, here's an example, is logging onto the Google Sheet. So you have to give IFTTN write access to your Google account. And if you have anything on Google that actually matters, you may wish to set up a second Google account, second Google email, a second Google doc to capture this spreadsheet. Okay, so there's a spreadsheet that's data log from the robot. I wouldn't start this one today because I'm about ready to upload if you go back to step, step 1 here, I'm about ready to upload another version, which includes the lab 4 version. It's in the same download projects. Step 1 probably is where it was. Yeah, there is going to be an October version of this. There's a link to this already on. There's a link to this on Canvas now, but as soon as I redact my my Google Fiber password, I'll post a new one. Yeah, so there's a, and then there's a lab 3 associated with open-ended, and Keyshawn did a open-ended one. They created me a new lab 3. I haven't yet edited it, but it uses the where'd it go? It uses the, where'd I put it? Put it here maybe? No. Put it in downloads. I'm about ready to create a new, yeah, here it is. That one, lab 3. A new lab 3 from Keyshawn and Aditya using this ESP32. But I haven't edited this yet, so I will. Is that the answer to your question, Austin? Yeah,
yeah, I guess I was more interested in the open-ended one. You said we could use like a Raspberry Pi or some other.
Yeah, sure. That's right. But that's already where'd it go? It's what to do with an open-ended is now you meant lab 3, right? So not lab 4.
Well, you know, lab 4 as well.
But. Yeah, but there is no. Okay, that's the wrong one. This one. There is a description on how to do lab 3 open-ended. I mean, it's kind of simple. It says there are 2 steps in doing an open-ended lab. First, you're writing me a new lab assignment for the rest of the class. And second, you're doing the lab, you know, yeah, sure. So, yeah, so you may want to work with, ask Keyshawn, Aditya, what, how they did open-ended. Yeah, I don't care. I'm interested in you. I'm interested in you learning the most you can. All right. So like I said, that was a great question, Austin. And you should have access to this folder. And oh yeah, this one is now done. I just finished it. Done, ready.
No, I do understand it, but there's yeah, it might need to be cleaned up a bit because it says understand the starter code for the open-ended project.
Yeah, that's just fine, whatever. Well, there is starter code. I mean, there we don't kid yourself. Regardless, you can't write anything from scratch in this class. All right. There's no bare metal in this class. So you are going to download starter code for your Raspberry Pi, whatever, for your thing. And I want you to separate, as always, the code that you write from the code that they download. Now, when student X does your lab later, there'll be more starter code, the Raspberry Pi starter code that you downloaded from the internet. And yeah, so you will download, sometimes you download, something in one format and you have to convert it to another format. Like I did with this lab 4. Basically I took, well, I'll get to it in a second. I took the Adafruit library and then it was written for the Arduino in C++, and I converted it to the MSP432 in C. Okay, that was my process. All right, like I said, I'm gonna introduce this new lab 4 so I can get it off my desk and to put it into checkout. Now, I physically bought, a year ago when I was planning for this class, 3 of these modules. But since it's really it runs on 2G, and since it is obsolete, in other words, completely dysfunctional at the end of the year, I only activated 1 SIM card and only built 1 project. And so if for some reason there's a whole bunch of you that want to do this all at once, I suppose I can activate a second SIM card. But there's only, so far, my intention was to, if you want to do text messaging, you'll just share this particular device and I'll just pay one monthly fee. Yeah, okay, so it's got a Adafruit module here. It's got an MSP432 launchpad, and just to make it fun, we talked about this sensor board back in the previous chapter, but I've attached it here onto the system to give you a potential suite of things that you could make a IoT station with. The light sensor, two temperature sensors, humidity, 9-axis IMU, and I actually don't have any code for the Hall effect sensor. It's functionally useless because the Hall effect sensor is here on the board and not next to anything that's interesting. But again, there's these suite of sensors that are on this booster pack. The booster pack's obviously attached onto the device. Let's see what else is here. It's got an antenna. I'm hoping I haven't asked anybody yet, but there's a couple of 3 professors on campus that actually know about antennas, and I will invite one of them to come give us a lecture on how it is these various antennas were designed. What was their basic thinking? But there are 2 USB cables. This one over here is basically used to charge this battery. It turns out when I turned it on this morning for the first time ever, this battery was completely dead. But luckily the system runs when you plug in both USBs. But this one is not for programming, that one's for charging the battery. So something in the system has to draw temporarily lots of current, and so this particular battery here provides current for the phone, whereas this one provides power to the 432 and to the digital side of this device, because there's the red line here is 3.3 volts going from here to there. Let's see what else is here. So breadboard, sensors. Sad part is this is gone. I think T-Mobile's announced they're going to discontinue its 2G the end of the year. So they make a 3G version, but it's also ready to be obsolete. So I thought I'd wait until I teach this course again and redo this lab. Anyway, there's the phone module. It costs about $40, $50 with all the parts. I think this is a fairly easy lab 4. I think, it will do full audio, phone calls, but that was not my intention. My intention was sending and receiving text messages. The starter code will send a text message. Your code, your job, if you choose to accept, is to receive text messages. If you could somehow figure out how to send less than a large number of texts, because it is a pay-as-you-go plan and not an unlimited text plan. That's my cell phone number. Please don't call me. But you can send me a text. Your machine can send me a text if you want to say when you're done. But I'm not going to go through all these commands, except you should look them up and figure out what they do. In this one of these starter codes, you'll see that basically I type in a message here, and then it sends response. Like I said, there's a whole bunch of these. I'm going to run this. Okay, let me talk about the tasks. One of the fun things about this project, as well as the fitness device, by the way, the fitness device, Bluetooth fitness device, also employs this RTOS. If you ever wanted to learn a little bit about RTOS, this is your friend, because this is the simplest RTOS you can possibly have designed, and you have all the source code for it. So if you haven't had 445M, that's okay. You don't have to know how it works. You just have to know how to use it. There is a logic analyzer built into it, except it uses the same port as the phone, right? The same pin numbers, right? The same port is used for SMS debugging and logic analyzer. So you can either run with the logic analyzer and not the phone, or run with the phone and not the logic analyzer. If you're running, if your system crashes, you may want to shut the phone off, run the logic analyzer, and see what happens. But this is a thread profile. Let's see, thread 0 is the real-time task running exactly every millisecond. And then threads 1, 2, 3, 4, 5, 6 are foreground tasks, which run at various rates. This ugly crap here is the Nyquist theorem. Since the logic analyzer runs every 10 kilohertz, it's sampled every 10 kilohertz. This is data that's toggling faster than 10 kilohertz. But you can see that these threads are approximately, thread 1 is approximately every 100 milliseconds. That's doing, where's my list here? Thread 1 is doing the phone. So it's looking for text messages or sending text messages every, don't send text messages 10 times a second, please, right? But it's implementing the text messaging there. Thread 2, they have each of the sensors is on another thread. So 2 seconds, 10 hertz, 1 hertz, 1 hertz, implemented there. Now the lab reads like all the other labs. Figure out the starter code by reading the data sheets and looking at the code, write some new code. And so the essence of lab 4 here, like I said, is the current starter code sends text messages. This is a suite of functions, 4 of which are not implemented yet, that read text messages. Okay, so on the other hand, well, I did copy paste the Arduino Adafruit C++ code for this architecture. Now you don't have to, you can do it, you can change whatever architecture you want, as long as you can send and as long as you can receive, figure out who the text message was from, and delete text messages. Okay. And then do something useful. Okay, this is kind of open-ended. It's kind of open-ended. I don't particularly care what use. It has to involve sending and receiving text. But again, there's a whole bunch of sensors on here that you could, like all the other labs I'm interested in. I'm not interested in bandwidth because that's expensive. Don't send me a lot of texts. But you can look at response time. How long does it take to send or receive text? Okay. The other fun thing to do, since this particular protocol was meant to run completely untethered, and so I gave in the kit's going to be a cell phone charging battery. There's a battery on it already. You could take this, don't take it out in the rain, but you could take this out in the woods, bury it in the dirt, and run it. Don't do it in the dirt, but you know what I mean. You could set this platform somewhere remote, so long as it's within cell phone tower, and have it do its thing. Okay. So in that regard, I'm interested in how much current the system runs. We talked about the power budget. If you remove this jumper right here, this 3B3 jumper, and put a current meter over it, you can measure how the current drain on this battery. Similarly, if there is a Yeah, there's, okay. There's a wire. Right here. There's a wire from the 3.3 volt lithium ion battery to the battery terminal of the phone device. And so you could put a current meter. It's just a wire. You can just current meter this connection. And then figure out how long the other battery will last. Apparently it drains power in the middle of the night when I should probably have been disconnecting that, but all right. So okay, so that's enough of what you're going to do. Let me do the demo. Yeah, that's okay. Demo. Okay, shut this off. All right. Obviously this is MSP 432 Code Composer Studio. Go to main. This program here is kind of fun if you're exploring the usefulness of the phone chip. This is basically a terminal program that you type in the terminal, type down here in the terminal window, and it basically echoes everything. UART1 goes out to the phone, UART0 goes back to the terminal. Okay. And so, yeah, this is the actual echo here. So anyway, this is a hello world one. Okay, basically it's going to send, don't send me all the text messages. Put your phone number there. Okay, put your phone number there. And this thing here will send a hello world to that phone number. Okay, so it's a fairly simple architecture. You give it a phone number, you give it a message, and you send a text message. And then this is the third main program you can run. Basically, again, give it somebody else's phone number, and then here you input a string, and then hit carriage return, and it sends the text message to that phone. If you had a real logic analyzer, you could profile this pin, but I haven't yet, so I don't know how long. And then this is the fun one. These are all the measured parameters that you could collect from that booster pack. Like I said, time, temperature, humidity, magnetic field, gyro, oscilloscope, acceleration, humidity. Task 0. In this operating system, real-time tasks get scheduled by the periodic interrupt, and they don't spin, block, or sleep. And so this is basically interrupt service routine. Think of this as an interrupt service routine, which just increments this time. Make sure this is hard real time. So make sure this is whatever you put in here, what's made way less than a millisecond, because it'll take down the whole system if you make this too big. And then the next 6 tasks are foreground tasks. They all look like main programs. So in other words, there is a set of functions to get executed once, just like a main program, and then a while loop that never finishes. Okay. And as you can see, this is basically the same thing as the other one. So this thread here implements the keyboard handler and the thread message. Okay. Again, change that. Don't send me text messages. All right. And then the other tasks are kind of, they're very similar, that implement the IO structures for the various sensors. There's humidity sensor, well, humidity and temperature, executing every 2 seconds, approximately, because this is not hard real time. This is not even soft real time. This is just approximately every 2 seconds. Then here's another one. This one's, the gyro is a little more complicated than the others because it's got actually 2 chips. But the program has the same structure. In other words, something that executes once, and then something that executes over and over again. Okay, and there it's reading the parameters from the 9-axis accelerometer at approximately 10 hertz.
So are the text messages sending that gyroscope data?
No, that's you get to do something completely weird. No. This text message is sending, I'm going to type something in right here. Let's see, where's test? I'm going to type right here. It does an in string, non-blocking. Okay. Which means that, I'm sorry, blocking. It's going to do a blocking in string, which means it will suspend execution if you don't type anything. So this particular thread is currently blocked because I'm not typing down here. But once I start typing, you see right here, it did the text, and you see it down there. Okay.
Yeah.
And so if I type something, oh yeah, let's quit this. Anybody want to divulge their anybody want to divulge their cell phone number?
I got you. You can do mine.
Okay, so just say it slowly.
My area code is 925.
925
487 1791.
Okay.
Hit me up, people.
Yeah, sure. Yeah, fine, whatever. Okay, build. And the last part is to put the sensors together with the text messages and do something interesting, like say, send it a text message that says, what's the humidity, and respond with the humidity. Or send it a text message and say, are you still alive? And it responds with how long it's been living. Okay. I don't know. I don't care. Just something that involves, all right. So down here, we'll just put in the date, just like we were doing some sort of Penn and Teller command here. All right. You should get a text.
Can I text back?
What? No, because I have no code. You could, but if you text back, it'll show up in the buffer here, and the first person to check it out will have to read it. No, I don't. That's actually the part I didn't write that you're writing, is the thing that receives text. Yeah, so yeah, don't text it back. But I assume from your smiling face it worked.
Yeah, it worked.
Okay, fine. Just
I've
ask.
also gotten text messages from people in the class, so this is
okay.
quite the experience.
Yeah, but not one from the embedded system. All right. So what was I talking about? I was talking about threads. Yeah, let me just review this particular operating system. You've seen this operating system before with the demo of the fitness device, but this is the initialization of the operating system. The clock's running at 48 megahertz. Oh no, there it is. It's probably done twice and only needed to be done once. Now the real-time threads have to be initialized separately from the scheduler. So this task got initialized once. It doesn't do much. It just sets the global variable to 0. Like I said, you can't both logic analyzer and phone at the same time. So in this case, I had the logic analyzer off. All the devices use the same I²C at the same baud rate. We've talked about why this is really 300 kilohertz and not 400 kilohertz because of the RC pull-up on the 10K resistor. Semaphores are an operating system device, and 1 means free, 0 means busy, and you'll see how it uses semaphores here. So here's a task that's using the light, that's using the OP3101 to measure the light intensity. And you can see that it will wait on that semaphore. And if it captures the semaphore, it will come through, use the I² device, and then signal it back. And compare this code to this code right here, and explain to me what wait and signal are doing in the context of I²C. How are wait and signal used here, frankly, over and over again? Okay, that was thread 3, and then, okay, this one's a little more complicated, but it still uses wait and signal. How is it using wait and signal?
I mean, it's just using them to prevent multiple processes from using the I²C bus.
This is unsafe, right? This is code that, okay, open declaration. Okay, so I²C E2, okay, open declaration. Okay.
Didn't you mention something earlier that the task had to return each task had to return in a millisecond?
No. Only the one tasks. No.
Oh,
okay. Let me finish this thought, Austin, and go back to the right here. You can see this is the lowest level I²C crap, and you can see I got there through whatever one of the devices, and you can see that this code does not disable interrupts. See that? Does not disable interrupts, which means it's got a critical section, because the thread switcher, okay, the thread switcher will automatically right here flip the like running at about a millisecond apiece. This real-time event will switch threads, okay? And so I could be right here anywhere in this for loop and get a thread switch, okay? And so, getting back to Austin's question, there are two types of threads: real-time threads or interrupt service routine threads, and foreground threads, which get scheduled. You see, if you look at the structure of this program, it looks like a main program, right? It never returns. It's got a while one in it. It never returns. And basically, yeah, even look at task 6, which is even less, okay? Stuff that gets executed once, and then stuff that gets executed over and over again, okay? And so the semaphore, basically, if the value of this semaphore is equal to 1, this thing will continue through. If the value of the semaphore, it will set it to 0 and continue through. If the semaphore is a 0, it'll block, so that the access to the I²C module is mutually exclusive, okay? That's what mutex stands for. It's a mutually exclusive way to synchronize multiple threads on a shared resource, okay? And so no, these threads, it's only thread 0. It's only thread 0 that has to be or task 0, sorry. It's only this one, because that one gets called inside the operating system. OS. That guy gets called, right? Where's my interrupt service routines? Right here now. Yeah, right here. This is a periodic timer interrupt, which will call task 0. And so it must finish within a millisecond, just like, just like any interrupt. All right, so we got semaphores. So this is a fairly simple use of a semaphore. We got wait and signal. We got sleep, which means don't bother me for 2 seconds. We got suspend. It was a suspend, which means don't run me now, but run me again whenever you feel like it. So this thread basically doesn't do anything. So yeah, over here, if you look at this, that's basically your free time. That's the available time that you could add more crap. When this thing goes to 0, when this thing stops incrementing, you're stuck, right? You've run out of CPU cycles. And this is the, now there is a FIFO. It's not used, but you could use it if you want. Let's see. And then these are the background, these are the foreground tasks. These are the scheduled tasks, 1 through 6. This particular, like I said, this particular operating system is very simple. Okay, it takes exactly 6 threads, no more, no less. So again, if you ever want to learn a little bit of real-time OS or review what you know about it, doing either this lab or the fitness device. Okay, so I'm just running. Yeah, see, so I guess I did my demo. Yeah, I did send my text. Yeah, any questions on this example? Now, just like all the other labs, I'm ahead of myself in terms of talking about the technology in 2G, as if that matters. Okay, all right, so stop sharing over here. Stop this. I will redact your phone number. So, well, I don't care. I'll leave it there. Anybody can text you. Where'd it go? Test 2. All right, save all. Stop share. Okay. Go over here. All right. In preparing for this lecture, I realized that the particular chip that we're going to talk about next is the HC12, which is one of the Lab 1 choices. And without getting my high-speed oscilloscope, I'm not really sure quite how it works because, well, anyway, we're going to do some more encoding schemes, I guess is the answer. Okay, can you see? Okay, can you see my slide? So, yeah, okay. So we're going to talk about the AC12. This was one of the Lab 1s. I think it's most fun, Lab 1, because it really does let you build your own interface. But what I want to do is really talk about some of the under the hood crap that works in the HC12. Going along, there's a new term that you'll see in the data sheet for these devices called DBM. The dB stands for decibels. The M stands for milliwatts. Okay, and it's a decibel. So it goes from what is 0 to 1,000 or minus 1,000 to plus 1,000 in logarithmic units, but it's meant to describe power. And as you know, the whole purpose of decibels is it allows you in a single scale to be able to describe things that are very different. So every you know, every 10 decibels is, you know, a ratio of 1,000, okay, or whatever, the log base 10. But it stands for decibels with reference to 1 milliwatt. Where's my pen? Okay. And in particular, here's the actual equation. When we talk about wireless power, right, we're going to talk about wireless power in milliwatts. All right, that's the output transmitted power. But when we report it, we're going to take the power, divide by 1 milliwatt, and then do a log base 10. So you know that my 10th grade science teacher is going to be very happy, because to take a logarithm of something, this here has to be dimensionless. Okay, so this is in decibels. Okay, why is it 10?
That's
Power.
the deci part.
Yeah, well, because it's in power. So if this were volts, right, or ohms, or amps, it would have been 20. Okay, but this is power. Yeah, it's the deci part. That's a good answer. That's where the I think the deci part actually comes from this 10 here, actually, to be honest with you. The log base.
I thought it was 1 bell is 1/10 of a decibel. So you have the
Okay.
10 up front. So everything is on the scale of like 0 to 100 rather than 0 to 1,000.
Okay. I asked a question for which I don't know the answer to. There are 2 10s in this equation, right? There's a log base 10 and there's a 10 here. Okay. I do know that this 10 is because what we're taking a ratio is power. Back when we looked at gain, voltage gain, or voltage, we used a 20. Right, for that spot there for voltage. And obviously it's meant for the whole decibel crap. I mean, it allows you to look at very large and very small values in the same scale. Okay, so you'll see some parameters, dBMs, in the data sheets. Now we use decibel without the M for things like signal to noise ratio. Okay. So there's our friend, the HC12. It was a very simple lab, very simple setup. It's in the sub-gigahertz range. You can see it's not in the same frequency as the CC 1352, which was in the 914, but this is at 433 megahertz. It's got a bunch of channels. It doesn't hop unless you ask it to hop. When people checked out, I asked them how they could detect collisions and could they hop or should they have hopped. It's got 2 big chips on it, a regular microcontroller and this Silicon Labs 4463. And so we're going to talk about the Silicon Labs 4463 because it's the one that implements. Now, interestingly enough, there's some tables here that I gleaned out of the data sheet for the device. Let me hide this so I can see the table. And it's got some terms that we already know. Between the chip, between the HC12 and the microcontroller, whether that's an Arduino or whether that's the MSP432, there is a UART here, a universal asynchronous receiver transmitter. And so it has a baud rate. It's talking about this baud rate here, which I do believe the starter code has it running at 9,600 bits per second. And it's going to send at 9,600 bits per second, it's going to send 15,000 pulses per second across the 433 megahertz channel. And so the actual data rate here is limited by the baud rate of the UART. Okay, so you can't send more data than the baud rate. And so as you increase or decrease the baud rate to the device, it will actually automatically flip over and use a different frame rate. When we talked about the Shannon channel capacity, was how many frames, how many pulses per second did you embed into the airwave, and you can see it will increase and decrease the frame rate in the air. An interesting sidebar has to do with what happens if you go faster. What happens at this rate, okay? And that is, it's going to, I don't know if it flips over with a different encoding, because we'll get to that in the slide, but you can see that the sensitivity, the ability to receive data changes, okay? And so from this table, what is the consequence of increasing this is the bit rate, this is the info, right? Because the information rate is the baud rate. Well, okay, at least it is 8/10, right? The actual bits per second in the actual bits per second across this channel is the limit or set here by the baud rate of the device, the maximum anyway, right? And what happens to this number as you try to go faster?
More power.
Okay. Okay, so this is sensitivity on the receiver. So it probably is more power, although I'm not sure of that, Austin. Okay, and it will be, the sensitivity goes down. This is worse. This is better. So if your receiving sensitivity goes down, what are you going to lose? What's the cost of going faster?
Less range.
Range, yeah, distance, this thing here. So like most trade-offs here, yeah, you got three things. You got bandwidth or information rate. You've got power, which you can either battery power or whatever, and then you have distance you can go. And so this thing here, even though, okay, somebody who finished this lab, you remember you didn't get 1,000 meters.
No.
No, this was probably the mode that would have given you 1,000 meters unobstructed. Okay, I'm just warning you that. Okay. What does channels give you, by the way? Why is this interesting?
You can channel hop to.
Yeah, it allows you to work in a more crowded field. If there are other devices out there, you could potentially find a quiet channel to use. Now it can't transmit and receive at the same time. Okay, and we'll see that when we get back to the book. Is you can't necessarily observe what you are transmitting. Okay. And so the way to tell whether or not you've collided is you could listen and see if there's anything on the channel, but you can't. The transmitter cannot detect a collision. Okay, the receiver can tell whether or not there's anything on that channel, but the transmitter can't. The transmitter sends something, and we'll see this when we get back to the book of how to channel hop. Okay, so here's some more stuff on, there's another setting, which is the same, kind of things, where you can do a trade-off between power and distance. And these are mode settings. These actually might be different encodings. I don't know, because I can't tell. They have not shown all of the code. I found the data sheet for this, but I don't really know what code is in here. So, and I found the AT codes, obviously, for these modes, but what they actually do, I don't know. We did have some fun when the kids who finished this lab about what the definition of transfer delay is. And basically you had in the transmitter, you basically send a UART packet out into the transmitter of one of these devices, and in a second device, not the same one, a second device, you get, so they'll call that transmitter 1, and then out of receiver 2, you get that same frame. And so, yeah, we had a discussion without resolution about whether this represented the transfer delay, or whether this represented it. I think because it's running at 9600 baud, this time here is not inconsequential. So that's about a millisecond to send 10 bits. And so I don't know what they counted. And I actually don't care how you, those of you that haven't done lab 1, I don't care how you measure it, as long as you define what it is you measure. Okay. And we're going to see where some of this delay comes from. And you can see some of these modes are wicked slow. Okay. And what do you suppose you get by running really slow?
Range.
Range, yeah. This is the long range, and some of these are low power, some of these are long range. Okay. Loop delay is defined where you have the second module. You got TX2 tied to RX2, and then you've got TX1 to RX1, right? So loop delay is the time between a TX1 and an RX1. And again, they didn't really specify, exactly how they measured it in terms of where they started, but that's what they meant by loop delay. All right. Okay, so yeah, luckily I found some spectrum analyzer output for this chip. It's 43 megahertz, right? Now the chip will support a lot of frequencies, but this particular embodiment of the HC12 is running at 433 megahertz. And it is obviously in decibels. And okay, so let me ask you the most important thing that happened out of Thursday's lecture. Okay, let me shut off the screen share here and look at your faces. Okay, the most important thing you got out of last time's lecture was what? We did the phase shift keying, right? And the offset phase shift key. What was the most important lesson from that lecture?
Minimize discontinuity.
Yeah, minimize the discontinuity. When you go from one pulse to another pulse, you have to. It's a single amplitude as a function of time, modulated at 433 megahertz. But as you chirp from one bit to another bit, you want to minimize the discontinuities, which force out of band frequencies beyond your 430, beyond your center frequency, in order to pack more channels in, to improve signal to noise ratio of the other devices. Yeah, so it's like the loudest guy in the room is the only one you're going to hear. And if they would just shut up for a while, other people can communicate, right? So that was the most important thing, is to, and so we're going to see it again. We're going to see it again here for some more encoding schemes. Okay. And it turns out it doesn't use phase shift key. It uses a combination of frequency shift keying and this on-off key, OOK, which is another amplitude encoding. So this is a phase shift key, which is basically going to, okay, yeah, and this is the spectrum of it. And if you were to describe the shape, look at the white one, okay? Look at the white trace. How would you describe it? Again, this is a single channel, okay? Right, with like a 3 kilohertz bandwidth here. So it's a pretty tight.
Got a center frequency and a.
No. Okay, look closer. Right at the center, what is it doing? The white, look at the white trace, not the orange trace.
Well, at the very center carrier frequency, it kind of dips. There's a
Kind of
shape
dips.
around the
There's
carrier
two peaks in
frequency.
there. You see the 2 peaks? There are 2 peaks. That's the ones and zeros. Okay, those are the ones and zeros. That's because the frequency shift key. Okay, click. All right. This is the amplitude shift key. We actually did this. We talked about this slide last time, where you amplitude shift and you have one or more amplitudes. This is clearly not the scale, right? Because if you took a 433 megahertz waveform and you sent 15,000 pulses per second, how many waves would be in a bit? Right, that's with over 1,000, right? There's 15 kilohertz versus 430 megahertz, right? So that's a couple of 10,000 cycles. So this is clearly some downloaded thing from Wikipedia describing the basic idea of on-off key and amplitude shift key. Now, we did the amplitude shift key last time. And again, I'm not sure exactly which encoding scheme. We're gonna have to get out some sort of high-speed spectrum analyzer on the HC12 to see how it actually runs. But assuming this guy, I got this off of All About Circuits. You see my reference, and it refers to the HC12. Okay. And so as far as I can tell from this is actual HC12 output. This is GSFK, which we're about ready to do, okay? Gaussian frequency shift key. 2 peaks with a very sharp window, okay? Which, as Austin reminded you, is the most important thing about encoding, is to have smooth transitions between the bits. So you don't throw off a lot of side lobes, okay? And so here's another picture of Gaussian. That's the red one. Okay, so you notice the shape of the red pulse here. Okay, with the sort of the hook'em horns kind of cat-like shape of the red curve here. this red curve here, this shape here, right? The cat shaped, it's 1 bit frequency shifted. And obviously this over here is not drawn to scale, right? Because these two frequencies aren't very far apart. They're both in the channel, okay? But if you just flipped from one frequency to the other, then you would get all of this crap out here, which is the bad stuff. And that is not a smooth transition between the 2 bits. So again, if you look at this red curve here, and you look at this white curve here, that's the only rationale that I have to say that what this particular chip is doing is a Gaussian frequency shift key, okay? Which is basically sending one frequency and then sending a different but close to frequency, shifting back and forth. Okay? And again, the purpose, and now Gaussian just means that they smooth the window. You know, and that's not. It doesn't surprise you that, you know, that the transitions right here, okay, is where the discontinuities are. And so it wave shapes these discontinuities in order to drop off the out of band components.
Why can't I encode more bits?
Well, you probably
with different
could.
frequencies? I have.
Okay, I don't know what 4G. I know, actually, I do know what 4G is. Yeah, you can. This is the simple one. Okay.
I have 400 kilohertz to work with, so like.
Why don't you? Yeah, I don't know. Yeah, it's a great question. Why don't you encode more bits? Because then I wouldn't be able to explain it to you. How's that? Okay, let's rewind. Let's rewind to what's the purpose of this protocol? What's the purpose of this subgigahertz? What application does this fit in?
GFSK.
Okay, what's the purpose of subgigahertz? Where does it fit in the spectrum of IoT?
Long and slow.
Yeah, long, slow, and low power. Okay, so this is supposed to be low power, long distance, low bandwidth. Okay, and so Austin, I'm guessing that if you encode more bits, it's going to incur more processing power. I'm going to guess that. I don't know that for a fact. That's my forte. But we started here because when we get to the other ones, I'm not going to be able to explain it to you because it's going to be way more complicated. In order to get, in order for your, right, for your, those high-speed Wi-Fis are up there in the billions of bits per second. I don't know how we're gonna figure it out. So we have seen 3 encoding schemes: amplitude shift, okay, and some of them are really simple, on and off. Phase shift last time, and now this is a frequency shift. Okay. Okay, so I am not going to explain to you how the decoder works, but we're going to play the little game here. Okay, we're going to go around the room, and you're going to look at the block diagram of the SI4463, and you're going to pick a module and explain to me what it does. And I'm going to start, okay, because that's the way we play the game. What is a Fifo for? What is a Fifo and why is it here?
Are you going to explain? You said you were going to start.
Yeah. Wait.
Yeah,
so are you picking
FIFO
it and then
is a-
we're explaining it?
No, yeah, I'm going to do one, and then you're going to, I'm going to do one, and then you're going to follow suit with another box and explain why it's there. Okay. So
Take VCO.
First in, first out. Okay. And it's a data streaming. It allows the sort of like an assembly line, allows the data to flow through this chip, not having, so this side of the chip and that side of the chip don't have to be completely in sync. Okay, so it is a flow thing. Now, judging from the data sheet, I don't think this this particular 8C12 uses the FIFO. Okay, but that's what a FIFO is. Yeah, somebody wants to do one. You only get to
I'll
do
take
one.
VCO.
Okay,
Oh.
okay, VCO. Okay, so do you want the whole square, or do you want what's a VCO?
I'll attempt the whole square just based on prior
Yeah,
knowledge.
what you do,
but,
since there's 9 of us in the room here, I'll assume you know the answer. Just tell me what a VCO is.
voltage controlled oscillator, you apply
Okay, so
a DC
now-
voltage and you get a different frequency out.
Yeah, no, unfortunately, there's actually no, yeah, so this is the input, the voltage, okay? And this is the oscillator, okay? Coming out. All right. I assume you know how the rest of it works. So I'm gonna let somebody else do some more.
I can do the mixer.
Yeah, so what does
yeah.
this do here? That's what you meant that, right?
Yeah, that's
Okay. What does the little X mean?
so the little X's are multiplying your signal that you receive from the low noise amplifier.
Yep,
And
times
that's actually
the-
going to basically demodulate your signal in the strongest sense of the word. That's
Okay.
multiplying it by the frequency. So you get a frequency copy of your signal centered at 0 hertz, which is what you care about, and 1 at 2 times the carrier frequency.
Okay, so now you got to show me what this, I guess you got to let somebody else do that. Okay, what's that then? That's
What you're pointing at is
important.
a filter.
No, somebody else. What's this box? It goes along with what he just said. So you get a copy and you
Yeah,
get
when
something-
you multiply your signals, don't you get some harmonics in there? So you want
Yeah, so what is this? What does this thing do? What shape is it, by the way?
Bandpass filter?
Look at the picture. Is that a bandpass? Look at the
Like
picture.
looks like my grade in this class.
No, just sideways. Yeah, sideways F. No. Yeah.
Low pass filter.
That's a low pass filter. Okay, to fetch off the demodulator. So these two are demodulated. Okay, these two would then be the demodulator. All right, somebody else, give me something else on here.
I'll take the good old ADC.
Yeah, there you go. Fair enough. I appreciate that.
Oh,
Analog to digital.
I'll take
Yeah,
the GPIO.
Okay, interesting. I don't know what the sampling rate is, although I do think it says how many bits it is, although I don't remember. Okay,
It takes
so
an
somebody else-
analog signal and converts it into the number of bits
Yeah.
specified.
How many channels?
2, I guess.
Yeah, it looks like 2, right? I don't know.
Looks like 2.
I don't know what the sampling rate is.
Is it 2 or differential?
I don't know the answer to that question. We're just playing a game here. There's an easy one here. Somebody want to do an easy, no one's pick the easy one yet.
Spy interface controller.
Yeah, there you go, SPY. Okay, so you're gonna know, I'm really happy it's not I squared C. Okay. SPY is very reliable. These two chips, as you know, exist right next to each other, right? This is SPY. Right, the clock goes this way, transmit data here, receive data, okay? Receive data, okay? There's another pin. Oops, going the wrong way. Yeah, you can see this also got the, these are the SPY signals here. It's also got a on-off signal, sure. Synchronous serial interface. It has the advantages of what? What are the advantages of SPY?
Directed communication with the master slave thing.
So this is a master slave configuration, right? This is probably the slave, and the other is probably a master. But it is, it's not really high speed, right? 10 million bits per second, but very reliable. All right. Okay. What else? Anybody else want to see one you want to
Did we
do?
talk about PGA yet?
No, but what's the PGA?
So I just Google it. I don't know, but it's programmable gain amplifier.
Yeah, it's a programmable gain amplifier, which means that it is, if the signal is low amplitude, what do you suppose it does?
Just
right?
gain.
It gains it, right? So it's got some it didn't actually show you the pathway here, right? But it will then sense the amplitude of the signal and then try to boost it before it converts it, okay? What is the problem? What is the trade? I mean, what if you boost the signal, what are you also boosting?
The noise.
The noise. So a programmable gain amplifier does not improve signal to noise ratio, okay? But it does improve the resolution of the A to D, okay? And potentially, and so as you know, most Wi-Fi devices will tell you signal strength. Have you ever seen that on your, the number of bars on your phone? What do you suppose, where in here is the number of bars, the signal strength? Right?
In the PGA, since we're talking
Yeah,
about it.
it's the input to the PGA, right? So the number here that you had to, the gain you had to set this up so it didn't, it didn't overthrow, it didn't, overshoot, it didn't, the ADC didn't overflow, is the signal strength, okay? And so, yeah, somewhere embedded in here is a value which is related to signal strength. All right, anybody, I don't know if anybody not answer? Yeah, pick another one. How about this one? We've done this one. What's that? Somebody who hasn't answered a question. What's that?
I was gonna pick LNA, the low
Okay,
noise,
fine. LNA, pick it. I guess fine. I'll let you do LNA.
the low noise amplifier.
Yeah,
is
that's an amplifier. Yeah, that's the receiver, right? That's a receiver. Sure. Okay, I don't mean to pick on everybody, but it's a fairly easy
Digital
one.
logic for 200.
Digital logic for 200. Yes. Yeah.
I'll take GPIO 0.
Yeah, there you go. That's fine. That's fine.
I'd
What do you
like to buy
suppose
a
that
ground
is?
pad.
What do you
Yeah,
suppose?
take
What do you
ground.
suppose these are?
GPIOs.
I know, but what do you suppose they are?
Oh, on the actual chip?
Yeah, what do you? They're general purpose input outputs, but what do you
Are
suppose
they
they're used
outputting
for?
on the chip or are they inputting?
Yeah,
What are
I
they
don't
programmed to
know.
do?
They're one or the other is the answer to your question. I don't.
Interrupt
Actually,
sync,
there is a data sheet.
synchronization,
Yeah,
like
so
interrupts for synchronization. I don't know.
interrupts. Well, there's already an interrupt pin. They're probably mode pins. I don't know. I actually didn't read them all. It's in there. How about this? What's that? You know what those are?
Isn't that the
Crystal
clock?
oscillator.
That's the crystal,
Yeah.
right? This whole thing is a phase lock loop, which is an analog circuit to get a smooth, clear, high stability square waves for the system. This
That's
is
how to find the carrier frequency, right?
carrier. All
That's the main scheme to find the carrier frequency, right?
probably. So it's probably controllable because the chip works at a lot of frequencies. This LDO stands for low dropout. Where have we seen that?
It's like a regulator,
Yeah, that's what type of regulator, man?
linear voltage.
It's a linear regulator. Yeah. So anyway, that's enough. That's enough game here. That's what I like to do when I open up a data sheet. See how much of it I can figure out without knowing much. All right. This I'm pretty sure they don't do, but this I schemed this out of the data sheet, and it was in the discussion of the FIFO. And because the way this chip actually works, okay, if you do this lab at 9600 at FU3 9600 baud, if you send 1 byte in the transmitter, you get 1 byte in the receiver, okay? And it doesn't seem like it streams the bytes together to send large packets, okay, with CRC fields. This is probably something the chip can do, which is not used for this particular embodiment. So that's the other trouble you do when you try to reverse engineer stuff. Sometimes it's way more complicated than or wait time, or more complicated than the data sheet. All right. So, okay. I don't know the answer to this question, so I'm going to pose it without actually knowing the answer. And so I'm putting this on the list of things that this professor. What time is it? Okay, I'm past time. Let me just pose the question, and don't ask me what the answer is because I have no idea. But a quarter is 24 millimeters. That I know, right? 24 millimeter. The red arrow here is a 24 millimeter distance, and the antenna that I bought with the HC12s is, I don't know, 22 millimeters. I don't know. It's something. I don't have it with me anymore, so I didn't measure it. But 433 megahertz is about 7 centimeters.
You got to stretch it out.
I don't know what you got to do. Let me just say, I don't know. I don't know what you're supposed to do.
Normally antennas are not the full wavelength. They're usually a fraction of the wavelength.
Yeah, so
like
is this a
half
quarter?
or a fourth.
Yeah, so I can't.
Yeah, but he's got to unspool it to get the true length of the antenna.
Okay, so if you've got this kit at home, don't pull the antenna apart because it works the way it is. And all the pictures on the internet show it coiled up like this. I don't know why, but I do know it probably matters. The shape of the antenna and the wavelength of the signal probably matters. Okay. And I'll have somebody come into this class and well, or somebody at least teach me that.
Yeah.
Anyway,
I think this antenna is resonant with a wavelength of half that. So it should be around 30,
okay.
35.
Okay. Well, and it may be what you're trying to tell me is it may matter. What you're saying is what you're actually asking me is it's maybe this distance. Is that what you just said to me? Maybe that's fine. Right?
Possibly. I'm not.
I don't know. Can I say I don't know? I say I don't know. It's yeah, I'm gonna get somebody's gonna explain it to me. And I know it matters. And it's not really the intent of this class to do antenna design, except, the antennas have to fit inside the box. All right, so we are I'll show you the software for the HC12, and then we'll go back into the chapter 5 and talk about more subgigahertz, Zigbee, the CC1352, etc. All right. Well, any questions? All right. So be safe out.